Hello everyone, welcome back. So in the last class we have seen what is GSW protocol. Let me quickly recall. So in this class we are going to see what is multi-key FHE of this GSW. Okay, so what happened in GSW protocol? As I told you, we are going to use something eigenvector, approximate eigenvector technique, correct? And we'll be using a gadget matrix to reduce the size of error. And the idea was, let us see the key generation. You have to choose a vector t which is then -1, and set your secret key as equal to -t comma 1, and uniformly get a sample matrix B, and your set B is equal to bt plus e. Your this matrix is your public key, where the first n coordinate, n-1 coordinate is this b, and the last coordinate is this b, small b, which has been obtained. It is similar to your LWE problem. And how do you encrypt? First sample a uniformly matrix R, and then ciphertext will be C equal to RA plus MG. Okay, then how do you decrypt? First find a vector W bar that is equal to all the elements 0 up to n-1, and last one is q by 2, and compute mu, which is C into S, inner product of CAS into G inverse W. And then I told you that CS will be this, and G inverse will be, I kept it as it is, go there, and at last if you multiply these two, G inverse W, so this part mg gs E inverse W. What do you know about S? You put the value of yeah, this is E inverse, this is G inverse W, so this will become MSW, and you know the W, every term is 0 except the last one, so I'll be having q by 2 remaining here, correct? So decryption will be easily possible. You just have to take mu upon q by 2, and that's it. Addition and multiplication was possible. Okay, now C2, the GSW scheme was making use of eigenvectors, correct? Eigenvector properties for the matrices. So because of involvement of gadget matrix, matrices, we have the following property. What is the property for a ciphertext? Ciphertext C, what is the property? If this C is multiplied with your secret key, what happens? I am having MGSI plus E. Sorry. Yes, so this is the property. That means I am multiplying my ciphertext with the secret key. This is what I am getting. Okay, so in the multi-key situation, similar should happen. In the multi-key situation, we would like to achieve a similar. Situation. okay, with a new secret key. New secret key, that is your joint secret key. So what is the secret key? I'll write S, this is equal to S1, S2, SK, K people, transpose. And then your ciphertext will be the, let me just denote it by C dash. The larger ciphertext I am having, and the gadget matrix will also be expanded. Okay. So like this I am denoting. And what is the condition it would satisfy? You see, this gadget matrix is just G multiplied by identity matrix of K. So this G will be on the here like this, G like that. So now what is the property it will satisfy? The new ciphertext, your C dash, if it is multiplied to the secret key, what you should get, just like in the previous case, the value should be M into the new gadget matrix multiplied by your secret key plus some error, say E dash. Do you observe something so similar I am trying to create? This was my secret key, correct? This was the error. This is the gadget matrix. So in the case of multi-key, I am having n parties, correct? Each of them having their secret key. So the combined secret key is this one. Okay. This will be achieved by transforming an existing ciphertext that encrypts a message M under a certain key SI into a new ciphertext encrypting message M under the concatenated key S. That means what? Earlier each party has encrypted. See, I am having P1 and P2. He is having his message, he is messaging here. He will encrypt it with his public key, he will encrypt it with his public key. Now I have to do the ciphertext expansion. That means I have to encrypt with a common guy which is similar for them. This is called ciphertext expansion. This step we are going to apply. So to achieve this, every ciphertext will carry additional encryption of the randomness matrix R used in the encrypted used to encrypt message M, which will allow the correct expansion to be performed. Once the expanded ciphertext satisfies the said property, whatever we had said on the top, homomorphic operation can be done on it as a single key GSW. So if we are able to expand this ciphertext C into some C dash, earlier it was C, I am able to make it C dash, and C dash satisfy this condition which I had just mentioned here. Okay, then similar to your GSW for single key, you can do the same thing for multi key also. Okay, so let us see a multi key setting for two party. So to achieve the multi key setting, two major changes are applied to the GSW scheme. To achieve the multi key setting, two major changes are applied to the GSW scheme. What are the two things? The public key of the participant, public key of the participants will depend on each other. That means the new ciphertext which I am having, that should be encrypted by the public key. That public key depends on each other. And as said, additional information is added to every ciphertext. Additional information is added to every ciphertext. Okay. So first let us see what is this public and secret keys, then it will be quite clear for us. Public and secret keys. Yeah, the public key of the participant will be related to each other in sense of a part of it will be exactly same. That means if the secret key, recall if my secret key is -t, 1, then corresponding public key was this one, b, this b, correct? For where small b is what? bt plus e. This was your Purdue, correct? And LWE assumption states that finding the secret key is hard when given the public key, correct? The crucial observation is that security will not be weakened if the same random matrix B is used for all the public keys for other participants also. Okay, what do you mean by that? That means for uniformly sampled matrix, B, which belongs to this Zn-1 cross M, okay, and for every secret key, key Si, which is -ti, 1, calculate small bi, which is bti plus ei. Okay, and the public key for each of the party will be, set the public key to be ai. What do you know about ai? It will be b and bi. That means first party, the public key will be b and b1. Do you see what is the special here? Each of the party is having this n-1 rows same. This part is same for each of the parties. Only the last row is different, which include the, which depends on your secret key actually. Yeah. Okay, now how do you expand the ciphertext? Let us see. This was the first case, public and secret key is done. Everybody has their public key and secret key. Next part is expanding ciphertext. So let us, so as I told you, let us first focus on two participant, okay, and then we'll extend it to the k parties. So suppose I'm having two messages. Suppose there is a message m1 and which is encrypted as c1. It has been converted as c1 ciphertext, and what do we want to do? We want to extend this as c1 dash. And what is the property it should satisfy? This c1 dash multiplied by s1 s2, correct, s1 s2 transpose, it should be m1 and then the gadget matrix s1 s2 transpose plus some e. This is the condition. Earlier what was the condition? It was just c1 into s1 was equal to m1 into gs1 plus some e1. This was the case here. Now this new ciphertext should satisfy this. That means it should depend on the both of the secret key. Yeah. So to observe this carefully, let us see the message. The message is encrypted with the public key A1, with the public key A1 and randomness matrix R. The expanded ciphertext, what is the expanded ciphertext? C1 dash will have the form like this: C1 some vector x, some matrix x, y, and again C1. This is how your C1 dash will look like. That is expansion of the ciphertext. And what is the condition it should satisfy? And we want it to satisfy the following. Okay, what was the condition? That is C1 dash multiplied with your S1 S2, it should give rise to let me just put the value C1 x y C1 multiplied with S1 S2, which is equal with which should be equal to m1 into the gadget matrix multiplied with S1 S2. Okay, now if you compare both the left hand side and right hand side, you are having two properties. First property is C1 S1 plus X S2 is similar to, this should be similar to M1 G S1. Second condition is Y S1 plus C1 S2, it is similar to M1 G S2. Do you observe? Now it is just the case that you have to find this x and y. You have to find this x and y, and what is the condition it should satisfy this new ciphertext? If it is multiplied with the combined secret key, joint secret key, the answer should be this. M into gadget vector, gadget matrix into S1, S2. I just solve it. Now I have to find the matrices. The one thing is matrices X and Y. One thing is very easy. Do you see the ciphertext C1 is multiplied with S1? If you put X equal to 0, then it is satisfying M1 GS1. Correct. This was the decryption protocol for the GSW. That means this C1 was encrypted with the secret key S1, and I just multiply it. It will be similar to M1 GS1. So from here I got to know that this X should be 0. One part is done. The second case is more difficult, but it is helpful to see what happens when trying to decrypt the C1 with incorrect secret key. Suppose, try to see that suppose the second guy, second party, he tried to decrypt C1 with his secret key. If he is trying to apply the wrong secret key to the C1. So what is the C1 actually? It is RA plus M1G, and I'm multiplying S2. So what happens here? It will be RAS2 plus M1GS2. Now what do you know about RA? Yeah, this is RE1. So what I'm having actually, do you see? I'm having this RE1S2 plus M1GS2. I wanted what? I wanted this part. I see. I just try to look at this guy. C1S2. C1S2 is equal to, I am getting M1GS2, I am getting, but I am having this extra term. So if you just try to see, if I take this guy this side, so I am having RE1S2 plus C1S2. Sorry, this will be minus sign, and this is equal to M1GS2, which I am having. So in short, what I have to see, can I relate this guy with this one, or can we find something related to that? And yes, we can do that. See, as we know something. What is E1 and what is A2? E1 is your B with this B1, and what is your E2? It is B with this B2. Correct. And what is your S2? It is minus T2 comma 1. Now we would like the term RE1S2 to actually be RE2S2. See this RE1S2, I just want it to be RE2S2. Then everything will be okay. Everything will look like in our hand. Okay. We would like the term RE1S2 to actually be RE2S2. Why do I want actually, if I have RE2S2, then I can easily combine with the second thing. Okay. And one more thing. And this would give a small error, while we cannot say anything about the size of RE1S2. I don't know how the size will it be. Okay. So this means that the actual and ideal term only differs a factor of R. That means, and let me just write, I'm having R E2S2 plus M1 GS2. Look at the right hand side, I am writing I'm writing this part, and re1s2 plus m1gs2. What I can do, I can just write r here. I can add a subtract, see, a2 minus a1 s2 plus r e1 s2 plus m1 gs2. Okay, what I have done, I have added this re1 s2 and I have subtracted it, this re1 s2. Now if you observe this r multiplied with e1, I'll be having rb and this b2, so I'll be actually having this part r b2 minus b1 plus, because this a2 minus a1 multiplied with s2, and here I am having this r e1 s2 as it is, plus I am having m1 gs2. Okay, yes. Now the challenge is to construct this r b2 minus b1 without knowing the value of r. This is the challenge. Can you find this? Whether any party can find this term. They don't know this b2 minus b1. And it turns out that there is a trick we can use for this. You can just write delta equal to b2 minus b1. Use a trick. Trick is write delta equal to b2 minus b1. Okay. Which can be done without any knowledge of the secret key, because b1 and b2 are parts of public key, correct? Because the public key, the last row, this is b1 and b2, so this can be easily done. You can get the value of delta easily. Okay, now let rij be the entries of matrix R and let participant 1, party 1 encrypt every one of them. Every one of them. Every element, this rij be the entries of R, and let the party 1, first party, what he did, he just encrypt every one of them with his b1. So how do they encrypt actually? That means, so a fresh randomness, by this b1 a fresh randomness occurs. Of this randomness, that is cuij. What is that? r dash v1 plus rijg. As I told you, I am just encrypting this rij with this new b1. which is sampled. Okay. Okay, and one more thing. Furthermore, furthermore let matrices Zij have entries all 0 except for the last column. Which is equal to the vector delta. Okay, so what I'm doing, let me just quickly summarize. The first thing is I want you to focus on this guy. Can we find this r b2 minus b1, because this was the extra term I was having. Okay, so for that what I did, I can find this delta, which is b2 minus b1, and r was publicly known, so let me write rij be the entries of matrix r, and let first party encrypt every one of them with the b1. That means a fresh randomness, that is uij is what, r dash b1 plus rij g. Furthermore, let the matrix Zij have the entries all zeros except for the last column, which is equal to the vector delta. So I am having, these are the content I am having. Now apply G inverse to get this Zij dash, which is equal to G inverse of Zij. Yeah, I was having Zij. What I am doing, I am putting this G inverse of Zij. This is similar to your GSW protocol where we were doing this part. So what will we have? So our Zij dash multiplied with uij multiplied with s1, it will be similar to zij dash multiplied with uij is what, rij g s1. Look at your uij. That's why I'm writing similar to. This is error term, so this won't be having rij into g. Okay. Now this is similar to, I can take this rij out. So I'll write rij here, and zij dash is what, g inverse of zij multiplied with gs1, which is similar to rij g inverse zij g, it will be just zij s1. Okay, which is similar to your delta. It will be similar to rij delta, because if you observe in s1 was minus t1 comma 1, and your zij is all the elements 0 except the last column, that is delta. So delta will be multiplied to 1. I will be having this delta side. Okay, now this was for one element, correct? So if this is done for all ij and put together, if this is done for all ij and put together the complete term, the complete term r into b2 minus b1 is equal to r delta can be recovered, can be recovered by multiplying with the secret key s1. By multiplying the secret key s1. You see, I just did one. So for each element I was multiplying s1 with that, but I observed that I am getting this delta. I am able to get this delta. So if this is done for all ij and put together complete term, your delta can be recovered without the knowledge of your secret keys. Okay. So fortunately this is exactly what we want. Since the intention to have this property, that is y into s1 plus c1 into s2 should be similar to m1 into gs2, and the term c1s2 differs about r into b2 minus b1 from the ideal outcome, m1 gs2. Okay. In conclusion, to find the matrix Y, we need the encryption of Rij and the difference between the keys B1 minus B2. In conclusion, to find matrix Y, we needed encryption of Rij, okay, and the difference between public keys. Difference between the public keys. That is B1 minus B2. That means what is happening here, thus say party 1 should include the encryption of Rij, should include the encryption of Rij along with the ciphertext C1, along with the ciphertext C1, producing a tuple of ciphertext rather than a single ciphertext. Producing a tuple of ciphertext rather than a single ciphertext. Then the expansion of ciphertext is C1 to C2 C dash means then the expansion of ciphertext from C1 to C1 dash means calculating matrices Zij dash and Uij. If you are able to find these two matrices and put it together to new ciphertext. So what is the new matrix? Here you are having C1, here it is 0 as I told you, x is 0, and here this is summation of I comma j, all your zi j dash ui uij and again C1. This is what your matrix is. And what was the condition? The condition was if you multiply this guy with your secret key S1 S2, yeah, look at the condition which I had asked in earlier. If this guy is multiplied with S1 S2, I should be remaining with these two, whether I am getting or not. Let me just check. If I multiply it with S1 and S2, what do I observe? The first term what I am having is this C1 S1. Second term I am having is this summation Zij dash Uij multiplied by S1 and plus C1 S2. This is what I am having. If you compare, this C1 S1 is okay. I had no problem with this guy. C1 S1 was giving me the value whatever I was required, that is M1 GS1. I wanted this to be M1 GS1. That is okay. What about this thing? I wanted this whole term, everything should be similar to M1 GS2. Now let us check whether it is satisfying or not. What I am having, let me just start with this summation Zij dash Uij multiplied by S1 plus C1 S2. Let it put the value. What do you observe with this first one? This Zij dash Uij S1, which is similar to Rij delta. This part is what? Summation Rij delta and plus I'm having this C1 S2. What is this C1 S2? I had already found out. Now look at this C1S2. C1S2 is this RE1S2 plus M1GS2. RE1S2 plus M1GS2. Okay, so I am having this M1GS2. I just want these two guy to be vanished. Yeah, and what is our delta? This is summation. Yeah, what is our Rij? Rij is the entries of a matrix R. Okay, and it was encrypted with the new randomness. So this will be Rij multiplied with your delta. Delta is what? It is B2 minus B1. Plus this is RE1 S2, and this will be as it is M1GS2. Okay, now observe. See, RE2S2 plus M1GS2 can be written as this RB2 minus B1 plus RE1S2 plus M1GS2. That means this is your delta. I am having R delta plus RE1S2 plus M1GS2. See, this is summation of this thing. This is, you can say, R delta. This is R delta plus RE1S2 RE1S2 plus M1GS2. Okay. Which is same as, so you got the left hand side. So this left hand side is same as this RE2S2 plus M1GS2. RE2S2 plus M1GS2. This is similar to. Now what do you know about RE2S2? This will be your error part. I am having, this is similar to M1GS2. M1GS2. This is what I wanted. I wanted that second term. It should be similar to M1GS2. This is what I am having now. See, whatever I wanted, I just wrote that and then started. I wanted this M1GS2 with RE2S2 instead of RE1. So I just try to see, suppose I'm having this, then what happened? I was having this extra term, R delta. So I wanted to reduce this without giving my secret keys. That means this delta I can find out. I just have to do this technique. Yes. See, including the encryption of this Rij will not weaken the security of the scheme because of the security of GSW encryption. Also, the expansion of ciphertext can be done by any party because no secret keys are involved, which is very convenient. See, in all the cases, I have not used my secret key anywhere. Correct. So each of the parties can do that. Now similarly, this was for two parties. It can be extended for k parties. So far, only two participants were involved in the multi-key GSW scheme, but this can be extended to k participant. The expanded ciphertext grows with the number of participants, but it will have the same form. Assume we are again given a ciphertext C1 encrypted with B1. This must be expanded this time to a ciphertext that can be only decrypted by the concatenation of all the keys. This expanded ciphertext, that means suppose in that case our expanded ciphertext will look like this. It will be C1 will be on the diagonal, and here I'll be having 0 0 everywhere, and here I'll be having some y2 y3 yk, and here it is 0. Okay, the first column contains the ciphertext C1 and the correction matrix, that is yj, that will give the correction factor r into b minus j. Because of this guy, I'll get this r into bj minus b1. Okay, when multiplied with the secret key s1. When multiplied with secret key S1. Note that these matrices can be determined just as in the two key scheme, only with different delta. That is, delta is bj minus b1 for different row j1. For every row I am having different. In general, for a message encrypted by participant I, column I will contain correction matrix yj for all j not equal to I, and the diagonal of the matrix will consist of the original ciphertext ci. Similarly, this can be extended to the threshold decryption. How will you decrypt it? The decryption is also very important. See, this multi-key scheme gives the possibility for threshold decryption. Every participant should do a piece of decryption with its own key. What happens? Every participant or party, every party should do a piece of decryption. Should do a piece of decryption with its own key, and these partial decryptions together make it possible. Together make it possible to retrieve the message. So to allow this process, we need the following lemma to make sure no secret key can be deducted from the ciphertext and partial decryption. To allow this process, we need the following lemma. To make sure no secret key is revealed, can be deduced from the ciphertext and partial decryption. Yes. So what is the lemma? That is smugging noise lemma. What this lemma says that uh, for I1 and I2 positive integer, for I1, I2 positive integers, and say E1 belongs to minus I1 to I1 and E2 say E1 is a fixed integer. Choose E2. E2 belongs to this minus I2 to I2 uniformly at random. Then the distribution of E2, is statistically indistinguishable from that of E1 plus E2 if B1 upon B2 is negligible of lambda. See now, now the adjusted decryption process can be described. So as I told you that assume, let us describe the decryption process. Assume we have a ciphertext C dash. We have a ciphertext C dash in the expanded form. Okay. Possibly you can say homomorphic computation have been performed on it. Okay. This can be seen as a vector of submatrices. This can be seen as a vector of submatrices. Submatrices say C dash, which is having M1 and Mk, okay, where every Mi is a column matrix. Now for all I belongs to the participant I, that is party I, first thing is he receives this Mi. Second, he computes Pi dash. What is your Pi dash? It is this Mi is multiplied with his secret key, and he is actually decrypting it with his secret key W dash. Okay, where W dash is a vector with all 0 entries. W dash is a vector having everything is 0, last term is q by 2. And the third point is what? Adds the smuggling noise. E belongs to ZQ. Set Pi is equal to Pi dash plus E. What I did, every party, or see the first party M1, the first party P1 say he received this M1, what he applied, his secret key with it, and then add some noise to it and send it to the. Finally the message can be retrieved. Finally the message can be retrieved from P, which is sum of all this Pi, I equal to 1 to K, through dividing by Q by 2. Dividing by Q by 2 and rounding correctly. Okay. So this mugging noise will make sure that every secret key SI cannot be deduced from MI and PI. This mugging noise will make sure the secret key SI cannot be deduced from MI and PI. Okay. The correct parameters with respect to the original noise and lemma must be used to generate this noise. Correct parameters must be used. So this was all about your multi-key FHE based GSW scheme. Okay, thank you so much.